Here's a signal from an ECG electrode. 1 millivolt. Your analog to digital converter needs 1 volt to read it. A voltage divider cannot help because dividers only make signals smaller. And if you connect this weak source to almost any load, its voltage collapses. Because the load draws current, the source cannot supply. So we need a device that can do 2 things at once. Read a voltage without disturbing it, and produce a bigger copy that does not sag under load. That device is the operational amplifier. Hold on to that starting point. Passive circuits attenuate. Precise amplification needs a new device. Let us meet that device. Physically, an op-amp is a chip. Conceptually, it is a triangle with 5 terminals that matter. A non-inverting input called the plus input, an inverting input called the minus input, 1 output, and 2 power supply pins, typically plus 15 and minus 15 volts. 2 conventions cause endless confusion. So let us clear them up right now. First, the plus and minus marks on the inputs do not mean positive and negative voltage, and they are not supply pins. They describe phase. A signal on the plus input pushes the output in the same direction. A signal on the minus input pushes the output in the opposite direction. Second, in most circuit diagrams, the supply pins are not drawn, but they are still there. Every milliamp the output delivers comes from those supplies, not from the inputs. So when the currents at the output seem to break the Kirchhoff current law, the hidden supply currents are the reason. Keep that in mind. It will save you real confusion later. One more fact about the device. There are no coupling capacitors inside. The op-amp is direct coupled, which means it amplifies DEC just as well as AC. So this part boils down to 3 facts. 5 terminals. Plus and minus mean phase, not polarity. And output power comes from the hidden supplies. Now that we know the terminals, the natural question is what the device actually does. The answer fits in 1 sentence. The output is the gain times the gap between the 2 inputs. Mathematically, V out equals A times V plus minus V minus. And watch the order inside that difference. It is V plus first, minus V minus. Write it reversed, and every sign in this course flips. The intuition. The op-amp is a difference machine. It subtracts the minus input from the plus input, ignores everything else, and multiplies that gap by an enormous gain, around 100,000 for a real chip. Let us feed it numbers and watch the mechanism. Say the plus input sits at 2.001 volts, and the minus input sits at 2.000 volts. The gap is 1 millivolt. The demanded output is 1 millivolt times 100,000, 100 volts, but the output cannot exceed its power supplies. On plus and minus 15 volt rails, it cannot pass roughly 13 volts. So the output slams into plus 13 volts and stays there. That behavior is called saturation, and the clamp levels are called plus and minus VSAT. Flip the inputs so the minus side is larger, and the output slams down to minus VSAT instead. Now imagine plotting the output voltage against the input gap. You would see a razor-thin ramp climbing between 2 flat ceilings. That steep middle ramp is the linear region, the only place where the equation holds. Remember that name. The golden rules will depend on it. So a bare op-amp, open loop, meaning no path from the output back to an input, is not an amplifier at all. It is a comparator. A 1-bit decision machine that simply reports which input is higher. If a problem shows an op-amp with no feedback path, your brain should instantly jump to one word: comparator. The output is plus VSAT or minus VSAT, decided by which input is higher. Do not write amplifier equations. And here is a common exam mistake. Reporting an output of minus 20 volts on plus and minus 15 volt supplies. Impossible. After every calculation, check the rails. 2 short anchors to keep. Huge gain. Unusable without feedback. And the output lives between the rails. Let us pause and collect what we have so far. The output equals the gain times the input gap. That equation is valid only in the linear region. The rails clamp the output, and no feedback means comparator. 4 facts. They carry everything that follows. With the equation in hand, we can ask why engineers model this device as ideal. Here is the trick for learning the list. Each idealization deletes one specific design problem. Learn it that way, and you never need to memorize anything. Property 1. Infinite input impedance. The problem it deletes is loading. If the input drew current, that current would flow through the 100 kilo ohm source resistance of your sensor. form a voltage divider, and corrupt the reading before amplification even starts. So the ideal op-amp draws exactly zero current into both inputs. This is golden rule 1, and you will use it in every analysis you ever do. If you remember only one phrase here, remember this: no current enters the input. And avoid the classic mistake, writing a current into an input terminal inside a current law equation. That single wrong term invalidates the entire solution. Property 2, zero output impedance. The problem it deletes is sag. The output behaves like a perfect battery whose voltage is set by the input. Connect any load and the voltage holds. That is why ideal gain formulas never contain the load resistor. Here's a way to keep both impedance facts in your head. Inputs are voltmeters. The output is a battery. Sense, without current, drive without sag. Property 3, infinite open loop gain. The problem it deletes is imprecision, and you will see exactly how in a moment. For now, hold the thought. Infinite raw gain is about to bias exact finite gain. A quick midpoint summary, because 3 properties is enough to juggle. No current into the inputs, a perfect battery at the output, and unlimited raw gain, waiting to be tamed. 3 down, 3 to go. Property 4, infinite bandwidth and infinite slew rate. Bandwidth means the gain stays the same at DSC or at any frequency. A real 741 runs out near 1 MHz, but the ideal has no ceiling. Slew rate means how fast the output can move. For the ideal op-amp, instantly. Property 5, infinite CMRR, the common mode rejection ratio. The formal definition is the differential gain divided by the common mode gain. Infinite CMRR means the common mode gain is 0. So the output responds only to the difference between the inputs, never to the level they share. Here's the example that makes it concrete. Both ECG leads carry the same 50 Hz mains hum. That hum is identical on both inputs, so it is common mode, and it subtracts away to 0, while the tiny heartbeat difference survives. A quick exam check. Raise both inputs by the same 2 volts, and the ideal output change is exactly 0. Property 6, zero offset voltage. Equal inputs give exactly 0 output. A real chip carries about a millivolt of internal imbalance. Multiply that millivolt by a gain of 100,000, and a real op-amp with its inputs shorted together sits at a rail, not at 0. For the 2 impedances, 1 compact anchor. Infinite in, 0 out. And one exam tip before we move on. If you are asked to list the ideal characteristics, give each property together with the problem it removes. That pairing is what a full mark answer looks like. So the whole list compresses to one line: infinite gain, infinite input impedance, 0 output impedance, infinite bandwidth and slew rate, infinite CMRR, 0 offset. Each one erases a specific error. Everything so far leads to one question. The gain is enormous, but wild. How do we turn it into something precise? The answer is feedback, and the next 3 minutes are the most important in this video. Start with a thermostat. You set 22 degrees, the room sits at 20. The heater drives, the gap shrinks, and heating stops when the error reaches 0. Measure, compare, correct. Negative feedback wires the op-amp into the same kind of loop. You route a fraction of the output back to the inverting input, the minus input. Now follow the mechanism slowly. If the minus input sits below the plus input, the output rises. The feedback path lifts the minus input as the output rises. The output keeps rising until the minus input equals the plus input. If it overshoots, the output falls and pulls it back. The loop has exactly one resting point. Both inputs equal. In other words, the output does whatever it takes through the feedback path to make its inputs match. Notice what made that work. The correction opposes the error. Now feed the output back to the plus input instead, and the correction reinforces the error. The output runs away and latches at a rail. That is positive feedback. And that is exactly why everything that follows demands feedback to the minus input. This distinction matters. We will test it again in a moment. Now let us make the idea rigorous. Take the defining equation and rearrange it. The input gap, V plus minus V minus, equals V out divided by A. Negative feedback stops the runaway, so the output settles at some finite value, say 10 volts. With a gain of 100,000, the input gap is 10 divided by 100,000, a tenth of a millivolt. Practically nothing. Now let the gain go to infinity, and the gap becomes exactly zero. The two input voltages are equal. V plus equals V minus. This result is called the virtual short, and it is golden rule 2. The imports sit at the same voltage. Yet, by rule 1, no current flows between them. Equal voltage, zero current. A short for voltage, an open circuit for current. That is why it is called virtual. And be careful about cause and effect. The chip does not connect its inputs. The feedback loop drives them equal. If you remember only one thing from this section, remember these two sentences. Feedback forces the inputs to match, and the whole derivation in one phrase. Finite output divided by infinite gain equals zero difference. Now, the number one op-amp error, the one this entire lesson is built to prevent, believing that V plus equals V minus always holds. It does not. It requires negative feedback, and it requires the output to be in the linear region, not saturated. No feedback. Feedback to the plus terminal or a saturated output, and the rule is dead. One more exam scenario. Suppose the problem gives you a finite gain, say 10 to the fifth, instead of infinity. Your brain should instantly jump to this. The input gap is V out over A. Small, but not zero. And the closed loop gain becomes A divided by 1 plus A times beta. Beta is simply the fraction of the output that the feedback network sends back. For the follower, beta is 1. As the gain goes to infinity, that formula collapses to 1 over beta. And the error of the ideal answer is roughly 1 over a beta, the anchor version. Closed loop gain is 1 over the fraction fed back. Let us lock in this section. The two golden rules, valid under negative feedback in the linear region. Rule 1, no current into either input. Rule 2, the input voltages are equal, or, in 6 words, no current in, no voltage across. With the two rules established, we can look at the special case you will meet most often. Ground the plus input. Rule 2 then forces the minus input to 0 volts. Think about what that means. A node sitting at ground potential with no wire to ground. That node is called the virtual ground. This is where students lose marks, so slow down with me. Input current arrives at the virtual ground through the input resistor. It cannot enter the op-amp. That is rule 1. It cannot flow into ground because there is no connection. It has exactly one exit, the feedback resistor. All of the current bends into the feedback path. Writing the current law at this node is op-amp analysis. That is the whole game. 2 more traps. First, hearing 0 volts and concluding that nothing happens at that node. Wrong. The entire signal current pivots there. Second, redrawing the virtual short as a real wire. A wire carries current. A virtual short carries none. Replace one with the other, and every current you compute becomes nonsense. So, before touching the golden rules, always run the validity test. Ask yourself 2 questions. Is there feedback to the inverting input? Is the output inside the rails? Yes to both, and the rules apply. Otherwise, switch to comparator analysis. And when you see feedback going to the plus terminal, a Schmidt trigger, for example, your brain should instantly jump to positive feedback, the runaway case. Output latched at a rail. Golden rules. Forbidden. 2 anchors to close the topic. The virtual short is earned by feedback, not built into the chip. And the 3-way triage. No feedback, comparator. Negative feedback, amplifier. Positive feedback switch. At this point, you might wonder how honest this ideal model really is. So compare a real 741 against the ideal, value by value. Gain 200,000 versus infinite. Input resistance, 2 megaohms versus infinite. Output resistance, 75 ohms versus 0. Bandwidth, about 1 megahertz versus infinite. Common mode rejection, about 90 decibels versus infinite. Does the gap matter in practice? Build an amplifier with a target gain of 10 using that real chip. The finite gain error comes out near 0.005 of 1%. Your resistors are 1,000 times worse than that. So the key idea is this. The ideal model is not a lie. It is an approximation whose error is usually smaller than your component tolerances. Use it by default. Now let us prove the rules earn their keep with 2 real circuits. First, the voltage follower. Wire the output straight back to the minus input and feed the signal into the plus input. Apply rule 2. The minus input equals the plus input, which equals the input voltage. But the minus input is wired directly to the output, so the output equals the input. Gain of 1. That sounds useless until you remember the impedances. Infinite impedance, looking in, zero impedance driving out. It is a buffer. It isolates a weak source from a heavy load. One line of reasoning, circuit solved. And notice something important. There is no virtual ground here. The minus input sits at the input voltage, not at zero. Virtual ground exists only when the plus input is grounded. Assuming 0 volts at the minus input of a non-inverting circuit is a classic lost mark. Second, the inverting amplifier. The signal flows through the input resistor into the minus input. The feedback resistor runs from the output back to that same node. The plus input is grounded. Step 1. Virtual ground. The minus input sits at 0 volts. Step 2. Rule 1 plus the current law. A current equal to the input voltage divided by the input resistance arrives at the node, and all of it continues through the feedback resistor. Step 3. Follow that current across the feedback resistor to the output. The output sits below 0 by that current times the feedback resistance. Here is the meaning before the math. The gain of this circuit depends only on the ratio of the two resistors. Mathematically, Vout equals negative RF divided by R1 times Vin. In words, the gain is minus the feedback resistance over the input resistance. Now notice what is missing from that result. The internal gain A has vanished from the formula. The circuit gain is set by two resistors you choose. That is exactly why infinite gain matters. It makes the circuit obey the feedback network exactly. Here is the shortcut top students use on every derivation. Write the minus input voltage using Rule 2. Then write the current law at that node using Rule 1. That two-step recipe solves the follower, the inverting amplifier, the summing amplifier, the integrator, all of them. So the method compresses to one line. Rule 2 gives the node voltage. Rule 1 gives the current law. 2 steps, every circuit. Let us bring the whole journey together. The ideal op-amp, infinite gain, infinite input impedance, 0 output impedance, infinite bandwidth and slew rate, infinite common mode rejection, 0 offset, or in 4 words, infinite in, 0 out. The 2 golden rules earned by negative feedback in the linear region. No current into the inputs, no voltage between them. Now test yourself. 4 quick questions. True or false? 1. The input voltages are equal in every op-amp circuit. False. Only with negative feedback, and only out of saturation. 2. Current flows into the virtual ground. False. It bends into the feedback resistor. 3. The output can exceed the supply rails. False. Never. 4. The follower has a virtual ground. False. Its minus input sits at the input voltage, not at 0.